In this video, we're going to talk about decision trees, specifically in the context of using machine learning to learn decision trees to classify data examples. And the basic framework we're going to study will be applicable to making continuous predictions or regression, but for now we're going to think mostly in terms of classification. So the outline of the video is pretty simple. We're going to go over an algorithm for learning decision trees, and then we're going to talk briefly about an extension to decision trees that anecdotally it has been known to be a very, very accurate machine learning method. So to start out, we're going to first go over an example of how a decision tree operates once it's already been built. So here's an example decision tree. So the first thing to consider is what is the decision tree going to get as input and what will its output be. In this case, this is a classification decision tree. So it's going to get a data example as an input, and then it's going to output a class label. In this case, I'm considering a binary classification problem where we're trying to identify a dog versus a cat. And at each node in the decision tree, we will consider one particular feature, and based on whether the feature is present in the data example, we will move to the left or right subtree. So for example, we could consider this as the input. So we see an image, or perhaps it's some description of this lion, and the first node is going to check the feature round ears, or it's going to ask, in this example, does the animal in the image have round ears? And in looking at the image, it's not really clear, but I would argue that this lioness does have round ears. So we'll move to the right subtree, and in the next level, the next node that we land at is going to check whether or not the animal has stripes. And because this animal doesn't particularly have stripes, we're going to move to the left subtree. Then we'll again check the feature at this new node, and the feature is whether the animal has a long tail. And the animal does happen to have a long tail, so we move to the right subtree. And at this point, we actually have a different type of node. So whereas the above nodes, I colored them in green, we'll check whether a feature exists in the example. The white nodes here at the bottom that are the leaves of this decision tree make a prediction. So at this point, the decision tree will output, oh, this is a cat. So it's a very natural way to imagine a classification algorithm working. It comes straight out of classical computer science ideas like binary search trees, but now we're working in multi-dimensional space, and we're discretizing the space, looking at binary decisions of whether to go left or right. And as you might expect, because of the tree traversal structure of such a decision process, this type of prediction algorithm can be implemented recursively and has a really, really simple body of the recursive function for prediction. So basically, it just looks at the current node's feature, decides whether to move left or right, and then recurses down to the left or right subtree according to that decision. So that's fine. But now what we're interested in is how to do learning when we have data that we have labeled and we want to then infer or learn the best decision tree possible for the data. So there's a number of ways to do this, and a lot of this depends. A lot of the variations depend on how we define what is the best decision tree for the data. But most of the methods for training decision trees are fit into a general framework. They fit into the framework where we basically start with a recursive learning procedure. We greedily choose the best decision rule possible to segment the data into a left and right subtree, and then we recursively train the decision tree for each resulting subset. So we split the data and then propagate it down and do recursively do learning on each subtree. So basic pseudocode for such a procedure is as follows, and let me walk through each particular step. So of course, this is the overall function definition where it's going to take in a data set, capital D, and it's going to take in the depth of the tree that it's currently at. And there's, at least in this pseudocode, I've written something kind of ugly, which is I have this global variable, which is in the next line, called max depth, which may or may not be as one of the inputs to the function as well. But this is a recursive function, and each call to the function will return a node which characterizes the subtree below that node. And okay, so now the second line that's highlighted right now, that indicates the base case for this recursion. So first let's think about the base case. So the simplest case, the situation where we don't do any recursion, is that we check whether the dataset D is all one class. So if we receive a dataset, or if D is our input to our current function call, and we examine D and it contains all cats, every single example is a cat, then we go into this base case scenario. And the other base case scenario is something that we do for practical reasons and for reasons that we'll discuss involving model complexity. We limit the depth of the tree. So if the depth of the tree is at the maximum depth, then we just run the base case scenario. And inside the base case scenario, what we do is we set the prediction at the node to the most common class in D, and we just return the node. Right? We don't put anything else into the node. Okay. Otherwise, right, if we don't go to it, if we don't satisfy any of these base case scenarios, we will run some subroutine to find the best decision rule. And another way of describing that is the best way to split the current dataset D, which we haven't defined here. We're just saying that some oracle is going to give us the best decision rule. And then once we have the decision rule, we're going to split the data by the rule. So we're going to form a left data set that contains all of the data points, all the examples inside D that satisfy the rule that we've found from the best decision rule. And then the right data set, or the right subset, is going to be all the data points inside D that don't satisfy the rule. Okay, so once we make that data split, we then recurse and form the left node, or we compute the left node by running this same function, fit tree, on the left data set with the depth increased by 1. Similarly, we run the same procedure on the right data set with the depth increased by 1. And of course, if that depth happens to be the max depth, then it will reach a base case, or if the D left or D right happen to be all one class, then we will also reach a base case. But we don't actually have to worry about that because that's the problem, the way you think about this recursively is that that's the problem of the recursive function call. We don't have to worry about it. We just look for whatever the node whatever the node will be that comes out of the fit tree procedure. So of course the critical piece and logic behind decision tree learning is the best decision rule subroutine that I've just left as just a essentially undefined function here. And most of the methods that have become popularized and have been shown to be very effective can be viewed as minimizing a cost function. In particular, what is defined as a good decision rule is one that creates a split in the data that minimizes some cost function. So you initially have some cost function over the full data set D, and then you ask for any possible decision rule. You say, well, what is the resulting cost going to be if we split the data according to this decision rule? And then you decide usually you just choose the rule that gives you the maximum cost reduction. So the 3 rules I'm going to cover are misclassification rate, entropy, or information gain, which it turns out those are equivalent, or something called the Gini Index, which is actually a form of expected misclassification rate. So let's look at each one at a time. So the first is misclassification rate. It's actually pretty straightforward once you spend some time to parse the mathematics, and I'm about to throw a bunch of equations on the screen, so bear with me. So the first is just a definition that we're going to use to make our expressions a little bit simpler. So the first is just this definition of pi hat, or pi hat for class C. So pi hat, of sub C is just the average of the indicator function for whether an example is in that class, in class C. And this is also the estimated probability, right? If we had infinite data, this would represent the exact probability, P of y equals C. But of course, we won't have infinite data, so instead this is just a class proportion in observed data. So the second equation is the definition for the best prediction given dataset D. And that is essentially just the majority vote of the most common class in D. So, for example, if we got a data set and it contained, 70% cat examples and 30% dog examples, then y hat would be cat for that data set. Okay, and now with that definition, we can then write down the misclassification rate. And this is the misclassification rate cost function, which it's also an average, just like above, but it's an average now over an indicator of whether the label is equal to the best prediction label. So, in other words, it's just if we were to just choose the majority vote prediction at this node in the decision tree. So going with that previous example of the 70% cat examples, it would be the error rate if you were to just guess cat at this node. And just intuitively, it's pretty easy to figure out what the error rate would be, and that error rate would be that you would be wrong on all of the examples that actually are dog because we're just guessing cat, and that would be 30% error or 0.3 error. So this expression lets you calculate that, and with some simple algebra, it simplifies to just 1 minus the class proportion of the maximum, or the maximizing class, or the best prediction class. Right? So it's 1 minus pi hat of y hat. Okay, so, and as I said before, what we're interested in then is, what split are we going to be able to come up with for this node that generates the best cost reduction. So we can write down that quantity, the reduction in cost, and that the cost, it looks like this. So you have the cost of the original data set D, and then you have the difference between that and the new cost. And the new cost is defined as a weighted average between the costs of the left data set and the right data set, as split by whatever decision rule we're considering. So we're actually going to use this bottom expression for all of our types of cost functions, but it's useful to see it in the context of this particular misclassification rate cost right away. And you can also stare at the expression for a bit and think about some extreme case examples, which help get some intuition for why this is a useful way of writing things down. So you can imagine if we had a data set where we could split things in such a way such that we get perfect performance, so exact prediction, and we're always correct on the left data set. And on the right data set, we still make some errors. So what we see if we plug in that idea is that the left data set, or the term corresponding to the cost of the left data set, would go to 0, and the right data set would be something that's a little bit less than what was currently what our original cost was. So you can see that that's a reduction in cost. Okay, so the second cost function we're going to consider is the entropy. And when we think of it, we're going to think of it as reduction in entropy, but it turns out that it's also going to be equivalent to, rather than finding the least entropic split, we could also imagine finding the most information gain, or the split that gets us the most information gain. And I'll go over these quantities. So once again, we're going to consider the class proportions, but for entropy, it's actually easier to think of this as an estimated probability distribution, just to make it consistent with definitions, formal definitions of entropy. So the Shannon entropy is defined as the negative expectation of the log probability, which is this summation over here, which sums over all the possible states of the y random variable times the log of that probability value and all negated. So we can right away just use this as this is the cost function that we're going to consider. And we just plug it right back into that same expression. And it works right away. This is exactly what we might be interested in optimizing. And you can think of it as this. The entropy is a measure of uncertainty. The higher the entropy, the more uncertain we are, or more precisely, the more uncertain the probability distribution is about the outcome of the randomness. So for example, if there's a probability distribution that has 1.0 probability of the label cat and 0 probability of the label dog, that turns out to have 0 entropy. And conversely, if it's 50-50, then that's the maximum possible entropy. That's the most uncertainty because we don't know anything. And then in between, essentially, the more peaked this distribution is, the closer it is to being completely deterministically one outcome, the less entropy there is. So that suggests that we want to split the data set into a way that lets us be very certain about the split subsets. So it actually turns out that the expression on the right of this cost difference, this cost reduction, that the proportional cost of the subsets, uh, when you plug in entropy for the cost function, you get something called conditional entropy, and that leads to an equivalence between maximizing the reduction in cost and maximizing something called information gain. And information gain is this expression here, which it turns out, like I said, it's exactly just plugging in entropy for the cost reduction up above. And the information gain is just a pretty simple idea. It's just how much information or how much uncertainty do you remove when you consider one particular variable in your random distribution. So if by considering a random variable we mean splitting um, a probability distribution based on observing a particular variable, then it becomes strongly related to the idea of splitting the data that we're doing in decision tree learning. So you can spend maybe 10 seconds to compare the two uh, equations on the screen, or the expression on the screen, the cost reduction of expression on the top right and the information gain definition on the bottom, and see that they're uh, the same thing when we plug in entropy as the cost function. So given this definition, this is actually one of the more important um, types of cost functions for decision tree learning, and this type of information gain measure becomes very important for feature selection or exploring data to understand the relationship between different variables. So it's useful at this point to then look at information gain and consider what happens with information gain when we have certain scenarios, certain extreme scenarios. So one scenario we might want to think about is the situation, the most informative possible situation, which is that xj equals y. And so usually we think about features as being somewhat related to y. There's got to be some pattern between the xj feature or the observable value xj and the true label y. But what happens if xj is exactly tells you what y is? How does this expression evaluate in that scenario? And then conversely, the opposite scenario is when xj is independent of y. So we'll work through these examples in class, but feel free to spend some time working them out on your own. It turns out to be pretty simple once you write it down the right way. Okay, so that was the second cost function. We had misclassification rate and we had information gain. And then the third type of cost function is something called the Gini Index, and it's one of these things that's been given a name, but really is just an expected misclassification rate, which is much more informative of a way to describe such a thing. So it looks kind of weird because it's got this squared term in it, but if you look at the left-hand side expression, it becomes pretty clear what's going on here. So essentially what this considers is the rate at which you'll misclassify data if you were to randomly choose a label according to the class distribution. So this differs from the raw misclassification rate because instead of just choosing the majority class, we randomly decide which label to predict. So to compute the expression or the quantity for the expected misclassification rate under this random prediction scheme, you have to consider essentially the combination of two events. You have to consider for each class the probability that we're going to predict that label, which is the class proportion, pi hat sub c, and that will be multiplied by the probability that c is the wrong label, which is going to be 1 minus the class proportion. So the left-hand side expression is pretty easy to intuit to be the uh, way of estimating the misclassification rate. And then through algebra, you can simplify it to the expression on the right, which is 1 minus the squared, or the sum of the squared class proportions. And actually on the right, you can also intuit that to be the expression because it's that summation is essentially the probability that you get the correct answer, right? Which again is the same idea. You have the probability of you guessing that label, and then the probability that that label is correct, which forms the pi squared or pi hat squared expression. So there's these three different metrics, and it's pretty challenging in the abstract to decide which is better or which you should use. And it turns out that they all behave relatively similarly. Um, and we can plot this. This is an image I took from the Kevin Murphy's book. You can plot this and see that they all have this peak of the maximum cost when you have 0.5 probability, specifically in a two-class scenario. So at 0.5 probability, you basically have no information, and this is considered a very high cost data set. And as you move toward either zero probability or one probability, essentially being certain about the label within a data set, you get less and less cost. And you might want to notice that the entropy in this plot, based on the code that generated it on the right, is not exactly at this scale. It's been rescaled in order to make it fit in the plot to view it all in the same area. But because we're going to use these cost reduction methods just to choose the lowest cost split, it's the proportions don't actually matter. It's actually just the comparison of the different values. So all this is the basic framework and the basic foundation for how you build a decision tree from data. But what we haven't talked about yet is the problem of overfitting, which is, I made a big deal out about going over that as the first topic of discussion for this course. So it becomes very important, or so it should be clear to you that I find it very important to consider this idea. So with a decision tree can achieve 100% training accuracy when each example is unique. So it's not too hard to see why this is the case. I mean, with an arbitrary number of decision rules, you can basically separate each data point into its own leaf and then predict exactly that data point's label. And usually you don't have to go as far as that to reach exact 100% accuracy. So one strategy, and this is with a decision tree with arbitrary depth and arbitrary size. So one strategy for limiting this behavior, is for preventing a tree from exactly memorizing the data set, is to limit the depth of the tree. And that's pretty reasonable. That's what I'm having you all do in the homework problem. But it's not the only way. And in fact, it can be wasteful if you limit the depth of the tree and then you find out later you need to go deeper. So another strategy which is pretty compatible with the idea of limiting the depth, is you just train a very, very deep tree, possibly all the way to 100% accuracy, or if that becomes that can be unnecessary if you just want to train a particularly deep tree that's not that clearly overfits, and then you adaptively prune the tree, which may be using strategies like actually pruning the tree um, by the particular branches, or just chopping it off very coarsely by each level. But in either case, one of the key strategies for pruning a tree or for deciding what size tree to work with is to use a validation set. So what you can do is you can just look at a decision tree that you've trained or that you learned from data and evaluate the prediction quality or the prediction accuracy of that decision tree on some held out validation set. And then what you can do is you can consider a deep subtree in your overall decision tree and see what happens to your validation accuracy if you prune that subtree away. So what you would do is you could just say, let's pick the majority class at this node, and for the sake of the example, suppose that's dog. So suppose if an input example has round ears but no stripes, then you just predict dog. And sometimes your validation accuracy will improve, sometimes it will get worse, sometimes it will stay roughly the same. But you could just choose some heuristics for when you decide a prune is worth it, because the pruning is going to save you computation time, as well as hopefully limit the complexity of your model, so you reduce the variance or the overfitting. So the last idea I want to present in this discussion is the concept of random forests, and it's this really cleverly named variant on decision tree learning, which uses something called bootstrap aggregation to train many decision trees. So this is in fact an ensemble method, and the idea is to take a data set and randomly subsample a bunch of subsets of your original data set. And what we're going to do is we're going to actually train decision trees on each of these subsets. And because these subsets are smaller than the original full data set, you actually would expect the variance to be high. You would more easily overfit the smaller data set than you would the larger data set. But that's okay for now. And what we're going to do is we're going to take that data set, we're going to train a decision tree on that subsample. But then we're going to do that many, many times. We're going to repeatedly pull out small subsets of the full data set and train decision trees on those subsets. And those decision trees will often be different. And they could be very different, or they may be slightly different. It actually depends on how big your subsets are going to be, or other aspects like how noisy your data is. But the basic principle is that by doing this many, many times and using the average or majority vote among the learned trees as the prediction, we actually reduce the variance, and we can almost reduce the variance arbitrarily by repeating it as many times as we need to, without needing to collect more data. So we have some fixed data set, and by repeating this procedure over and over again, getting more and more trees to average over, we can effectively reduce the variance without making much of a change in the bias. And additionally, we can also randomly subsample features to try to control how much we overuse a feature. So that's the whole recipe for the random forest idea that has become fairly popular. And the promise is that it is a way of reducing variance without changing the bias. But this basic concept of bootstrap aggregation, or bagging as it's been nicknamed, it can be applied to a variety of learning algorithms. But one of the particularly interesting pieces about applying it to decision trees is that decision trees essentially kind of arbitrary complexity. They're if you don't limit the depth, which we still might also be interested in doing in this procedure, but if we don't limit the depth, they're fully non-parametric and fully can grow to the complexity to memorize any data set. But now if we do this ensemble idea where we're now memorizing a bunch of different subsets, randomized subsets of the original full training set, we can eventually reach a predictor that is fairly robust and it doesn't overfit as much as each individual model does. So to summarize what I talked about in this video, I talked about how to train decision trees. I gave the basic overall recursive framework, and I showed you that the main difference between most methods of decision tree learning is what cost function to use within that framework. And then I talked about 3 particular cost functions, and there are others. There are others out there, but the ones I talked about were misclassification rate, the entropy, and the expected error, or the Gini index. Then I talked about how you do pruning to adaptively reduce the overfitting using a validation set. And finally, I ended with the idea of using random forests or bagging to produce a more robust classifier based on many combined decision trees. So one thing you might notice about this video that's different from other places that introduce how to train decision trees is that I didn't really give names to the learning algorithms. Historically, they have some pretty famous names like the ID3 algorithm and the C4.5 algorithm and the C5.0 algorithms. And these names are not particularly informative, so I left them out. But they do map to some permutation of the concepts I've introduced in this video, with the exception that, for the most part, I've left out the concept of continuous data. I've mostly been considering discrete data, although this whole framework is pretty vague about what the space of possible splits is that you search over. And when you deal with continuous data, most of the strategies for handling continuous data involve being more continuous about how you decide what your splits are. So not only do you decide which feature you want to consider, you also consider different thresholds for the features. And the same would need to be the same idea would need to be applied if we were to extend what I showed you in this video to non-binary features. So if the features are discrete but multinomial, so there's like k different values for each of them, then you might have a situation where you maybe split the tree into k subtrees, or maybe you would group the different values into 2 possible sets of candidate values. So there's different strategies for handling different data types, but they all stem around the basic recursive idea that I introduced in this video.